Physics 2018, welcome back to part 2 of the Unit 5 study guide. In case you didn't see the note on the last video, I made a mistake at the very end of number 6. I had that 166,600 divided by 85 gave you a ridiculous number, which admittedly I probably should have noticed. Didn't make any sense, but I was kind of rushing to hit that 15-minute mark. This program only lets me record 15 minutes at a time, so that's why I was rushing towards the end. So this is actually divides out to be 1960, which then when you take the square root gives you a final answer for number 6 of 44.2. So just to clear up that little bit on there, I believe that once I get this uploaded to you all, it will have the correct answer. So just in case you get confused, that's what happened. All right, now I said I was going to go to number 7 next. So calculate the K constant for this bungee cord. All right, so at first glance, you might look at the problem and be like, okay, what the heck do I want here? Well, a K constant only ever appears in one equation. So when in doubt, go check your formulas. You're looking for K. This is what you want. So up here in my stuff, looking in the conservation section, so in all of, whoa, don't do that. Don't do that. In all of this stuff, the conservation part, there is only a single, okay, let me take that back. There are two Ks. There's capital K, but all that means is kinetic energy. So that's not what we're looking for. But if we keep going down here, aha, there's a K. And I even put a note in my version of the formula sheet, K is the elastic constant. And that is what we're looking for. Calculate the elastic constant. So in the elastic energy equation, that is what we're going to be using. So clearly we need some place where we have the elastic energy. So let's go back to what we were looking at before. We had elastic energy in two places. We had it where the cord was stretching, and we had it here at the very bottom, where he stops moving. So this bungee jumper has two different places where we could work with this. Which one's going to be easier, though? So in this area, we still have some kinetic energy. We know what our total is, so that's not going to be a problem. We know that all of our energies need to add up to this 333,200 joules. But in this case, in that section where the cord is still in the middle of stretching out some, we have to know how fast he's going. Because the only thing that we can't... Sorry, back up. Since we're looking to find K, we have to know absolutely everything else. And in this case, since K requires the velocity, and I don't have any information about velocities in the entire prompt of the problem, I can't do this. Because then there would be two things that I don't know. There would be the velocity, and then there would be the stretch. Or the K constant, I mean. Actually, there would be three things I don't know. Because in that elastic energy equation, we need to know X. X being the stretch or compression of the bungee cord. And unless I pick a specific spot, I wouldn't know that either. So we got too many problems in this area. But here at the bottom, where we only have two energies, we have the lowest amount of gravitational energy and the maximum elastic energy. That's probably what we're going to want. So we know that the gravitational plus the elastic is going to equal our total mechanical energy of 33,200. So that should get us to a pretty good place. So let's just fill that out for now. So we got 333,200 equals GE plus KE, or no, sorry, elastic energy, EE. So that's going to be 333,200. Just going to fill in the equations just for, like I said, you want to do this just to make sure that you don't make any mistakes. So 1/2 KX squared. All right. Now remember, like I said up at the top, K is the elastic constant. That's what we're looking for. So that's going to be an unknown for sure. So that means we have to know what this X is, what the amount of stretch distance is in meters. And fortunately, they most certainly gave us that in the problem. They said that eventually stopping him once it reaches a stretch of 40 meters. And that is what we're talking about. We're talking about the point where he stops. So that 40, that's X. That's what that is. That's how much it stretches. So I can plug that in as my X value. And everything else I know. The height, remember, it took a second to figure that out, but we did figure it out. That is at 60 meters is the height, because we had to figure that out. We had to do a little doing. We had to think about the fact that at 100, that the cord started to stretch, and he's still falling, so it's going to be down further whenever it stretches out. And it stretches by 40 meters. So if the cord stretches 40, then you have gone 40 farther than where you were before, which was at 100. So you're down at a level of 60 meters once it's stretched all the way out to its maximum 40-meter stretch. So that's how we did that. That is a very common thing that'll happen in physics problems, is you'll have that little extra step where you have to do just a little bit of a leap in logic. You can't just take the numbers and plug them in. You have to actually think a little bit. And I know that that's a problem for some of you. So try to develop this habit of this mathematical thinking. Don't get frustrated. Don't give up. Absolutely don't give up. Actually look at these and just break it down. Say, okay, what do I know about the situation? What's going on? Where can I get the information that I want? And it is a difficult skill. I'm not going to lie to you. This is junior level science. It's supposed to be hard, but you can do it. It's not out of anybody's range. I'm 100% believe that, or I wouldn't be in this profession. You can get this stuff down. All right? Know that I believe in you. All right, I'm not going to do all that kind of like amping people up kind of nonsense. I'm not good at it. So let's just keep going with the problem. 33,200 equals 170 is my mass, 9.8 is my gravity, my height is 60, plus 1/2, k we don't know, and then x is going to be that 40-meter mark squared. So now we just do algebra again. If it's all the same to you, I'm just going to work out the answer here on my calculator just to save us some time. So 170. I'll talk through what I'm doing, but I'm not going to actually type it. 170, because I believe that you all can figure out the algebra or talk to somebody who can show it to you. So 170 times 9.8 times 60, not 6.60. Okay, so that gets subtracted off of the total, so 99960. So that minus 99960 equals, okay, so I have 233,240 here is, and then what's 1/2 of 40 squared? So 40, stop calculator, 40 times 40 equals 1600, and half of that is going to be 800k, and then divide through by the 800, so we'll get 233,240 divide 800. Gives us an elastic constant of k equals, stop capitalizing, I don't want that capital, equals 291.55. Now k does have units, but they're really ugly, so basically they're the units that make the equation work out to what it's supposed to be. So it's like joules divided by meters squared, but it's a constant. The units are not important. They work out to make it a correct equation. So it's 291.55. It's a constant. There you go. There's your answer. All right. So keep in mind that whole deal. The reason that we had what we had at the start, we decided that the total energy, remember that's what that was. That was the total energy, total mechanical energy, was GE plus EE, because that's what we had at that place, and that was the easiest position to actually calculate the thing that we wanted. We wanted the K constant out of the elastic energy. All right. Now, number 8. This is kind of an extension of number 4. How does the situation change if they jump off the bridge instead of just falling down? So basically, all that's going to do is add something to the beginning. So at 200 meters, in this case, let's just consider this. At that 200 meter mark, you're going to be jumping. So at 200 meters, we're jumping, so that means that we have jumping upward, and then my little bar. So that means that we're going to have KE and GE. We've got that gravitational energy from being on the bridge, and we also have some upward kinetic energy. Right, so now above 200. So somewhere above 200, we're going to be slowing down, but still going up, right? So that means that we're going to have decreasing KE and increasing GE. Kinetic energy is going down because once you jump, you slow down. And then your gravitational energy is increasing because you're going even higher. And then at some max height, without doing like the old kinematic equations from the beginning of the year, we can't figure out how high it actually is. But at that maximum height, he'll stop, right? He'll stop and then start to come back down again. So we'll have a max gravitational energy. That'll be a bigger maximum than we had before because we've added some energy to the system. So it won't be, this is another change that you could point out, it won't be 330,200 anymore. It'll be a little bit higher than that. It'll be adding on that original kinetic energy to the original gravitational energy. That gravitational energy is still what it was before. I mean, we haven't changed the actual, like, original height. It still starts at 200. And that 200 is still going to give you this much gravitational energy. That's still true. But now the problem is, at the very beginning, we have an additional kinetic energy term. So ultimately, the answer to this is you're going to have some extra energy total. And then you'll have some extra stuff going on at the beginning of the situation. So he'll go up a little bit, kinetic energy decreases, gravitational increases, he'll stop, and then he'll start to come back down, and then everything else is exactly the same. Almost exactly the same. So he'll fall back down to the 200 mark, and he'll be back at the same energy that he had right here, because he's at the 200 mark again. So he'll go up, come right back down, be at the same speed, because energy is conserved. We're ignoring air resistance. So he's not going to be slower coming down than he was when he was going up. It's going to be exactly the same. It's going to be a parabola. You know, you've seen a parabola. It's going to go, watch the mouse. It's going to whee and back down. All right. Can't believe I just went wee on a stupid video. All right. So that's that problem. All the way 1 through 8. That I feel like was the hardest one there for the beginning. These next couple of problems are pretty simple. They're just generic energy calculations. This one uses gravitational, this one's kinetic, this one's elastic. They're all pretty basic. Define work, you all can do that. Let's see, where's the next hard one that I wanted to show you? This one's not bad, this one's not bad, this one's not bad. Go back and look at the old work assignment that we did towards the beginning. Okay. Here we go. This was the next hard one. Alright. So, Stan uses a spring-loaded cannon to fire a 3-kilogram ball. Spring is compressed 0.75 meters and has an elastic constant of 15,000. Jan does 30,000 joules of work throwing a similar baseball. Who will have the higher launch speed? Okay. You got to think about this in two different pieces here. So, oh crap, stupid numbers. So next up we've got, first let's think about Stan. So Stan uses a cannon, and then it fires the cannon and it makes the kinetic energy. So launch speed, that's going to be based on how much kinetic energy that it has. So think about conservation of energy here. He's going to start off with elastic energy, because, you know, spring-loaded, that's probably elastic energy. And then it's going to turn into 100% kinetic energy. So you can consider the fact that, yeah, he's probably like holding the cannon up in the air. So the gravitational energy is there, but it's not relevant to the problem. So he's going to fire the cannon whether he's holding it or whether he's got it on the ground. And the ball's going to come out of the cannon at the same speed, whether or not he's holding it in the air or holding it on the ground. So the gravitational energy is completely irrelevant to this point. So all of the elastic energy from the cannon is going to turn into kinetic energy. So EE from the cannon, I'm going to do a little subscript, cannon, okay, equals, whoops, whoa, don't do that, equals KE launch, whoops, launch, right. So that's for Stan. And then for Jan, she is going to do work instead. So now we need to jump into our work equations. So remember, work, that's the whole force times distance thing. It's where you put energy into a system. Jan is going to literally push the ball with her hand. You know, that's how throwing an object works. And here's the connection. Launch speed, work. Work equals, boom, work. Here we go. This is what we want. Work equals delta KE. Delta means change. Don't forget that. Work equals change in kinetic energy. It's literally just saying that from throwing the ball, the amount of kinetic energy it's going to gain is equal to the amount of work. So we literally can just say that the work that she did, whoop, I passed it up, the work of 30,000 joules, that is the kinetic energy. So the work equals the kinetic energy for the launch speed. Boom, done. And once again, I'm out of time for this video, so I'm going to pick up in the middle of number 18 in part 3. So if you are confused about number 18, jump to that.